Hello everyone, today we'll be talking about Jablonski diagrams, what they are and why they're useful for the fields of photochemistry and spectroscopy. Jablonski diagrams are tools used in molecular spectroscopy that show the electronic and vibrational states of molecules, as well as the possible transitions between those states. These states are arranged by energy on the vertical axis and grouped horizontally based on spin multiplicity, or the total number of degenerate spin states. These diagrams show the possible transitions between the states, with radiative transitions shown with solid lines and non-radiative transitions shown as squiggly lines. Radiative transitions include absorption, fluorescence, and phosphorescence. Absorption involves a molecule absorbing a photon, which excites an electron from the ground state to an excited state. Fluorescence involves an electron dropping from the lowest vibrational level in an excited singlet state back to the ground state, thereby releasing a photon. Phosphorescence involves an electron dropping from the lowest vibrational level of an excited triplet state back to the ground state, releasing a photon. This is spin forbidden, so it takes a lot longer. Non-radiative transitions include internal conversion, vibrational relaxation, and intersystem crossing. Internal conversion involves a molecule in the excited state reaching a point where the electron distribution and nuclear coordinates are the same as a molecule in the ground state. This allows a molecule to go back to the ground state and shed, in the process, it'll shed excess energy as heat through vibrational relaxation, which occurs when a molecule loses energy as heat and goes to the lowest energy vibrational mode within the same electronic state. Intersystem crossing happens when a molecule transitions to a state with a different spin multiplicity, like excited singlet going to excited triplet. This requires spin-orbit coupling in order to conserve spin, so the orbital configuration typically needs to change in a way that keeps the total spin conserved. Tracing these steps through a photoexcitation event, first the molecule absorbs a photon, getting promoted to an excited vibrational state within an excited electronic state. Rapidly, it will shed excess energy as heat and vibrationally relax to the lowest vibrational state of the excited electronic state. Then it will either undergo fluorescence or internal conversion back to the ground electronic state, or it will go through intersystem crossing into a different electronic excited state with a different spin multiplicity. From there, it can undergo phosphorescence or another intersystem crossing to get back to the ground electronic state, and after returning to the ground electronic state, the molecule will once again go through vibrational relaxation. Jablonski diagrams are a useful heuristic tool when studying and learning about photochemical processes. The process of a molecule interacting with light is a very complicated dynamical physical system that requires quantum mechanics and quantum field theory in order to actually accurately describe. But for a lot of these things, we don't need a super accurate description. So the Jablonski diagram simplifies the system and distills out key components of chemical relevance into a graphical form. By providing a general map of these processes involved in photochemical systems, the diagrams aid in chemical intuition and makes brainstorming and research more efficient.